Hello again, everybody. It's me, Mr. Younger. I'm solving another rotational kinematics problem here. So let's get started by me sharing my iPad screen. So as you can see, the question here is, it starts off, centrifuges are used to separate parts of blood from one another by density. If such a centrifuge is allowed to accelerate for 30.0 seconds from rest and is then found to be spinning at 25,000 revolutions per minute, what is its average angular acceleration in RPMs per second and in radians per second per second? Also, through how many revolutions will it have turned? So that's the actual problem we're going to work. Let us begin the solution as follows. So solution, what we're working here with is some information. We know, for instance, the angular velocity initial is 0. We know the angular velocity final, which means that after 30 seconds, is equal to 25,000 revolutions per minute. And I'm writing it revolutions per minute as opposed to RPM so that we can make easy conversions and knowing exactly what's going on. So that's omega final. We found the time elapsed was 30.0 seconds. And what we're asked for is the average angular acceleration. So we want alpha bar is equal to question mark in 2 steps of units, of course. And we also want to know theta equals question mark. We can make the assumption that theta 0 is 0, just like setting the origin of time being 0 or setting t0 equal to 0. We can always set the initial angle to 0, and that would allow us to just calculate the total angle turn. So let's start off with computing the average acceleration first. We do know an equation that we could use for that, for instance, is just like it's the rotational analog of the average acceleration equation. The average linear acceleration equation is v final minus v initial over t final minus t initial, which we normally just call t. So I'm going to say the rotational analog of that is alpha is equal to omega final minus omega initial divided by t minus t0, and that's our average angular acceleration. That's going to give us 25 times 10 to the third. I'm assuming here that I only have 2 sig figs in the 25,000, but I'll carry extra digits, so it would be you'd have the result even if you did 3 sig figs. So that's 25,000 revolutions per minute minus 0. And then all of that is divided by 30.0 seconds. And we get 25 divided by 30, 25,000 divided by 30 gives us 3 sig figs. To 3 sig figs is 833.3. And I'll put another 3 here. So this one, we actually technically only have 2 sig figs, so I'll just leave it here. And that turns out to be in revolutions per minute per second. So that's one of the answers. And what that tells you is it increases by 83.3 revolutions per minute each second. So at 0 seconds, it'd be going 0. At 1 second, it'd be going 833 revolutions per minute. And then at 2 seconds, it'd be going 1667, and so on and so forth. Now, I also asked for us to calculate it in radians per second. So our radians per second per second. So to do that, I'm going to take the alpha in RPMs, which I said was 833.3 revolutions per minute per second. I'm going to box that off. But now I'm going to make use of it and say alpha in revolutions per minute per second is equal to 833.3, and that would be revolutions per minute, and then divided by a second, which means just having a second in the bottom like here, like this. Now, what I do know is I want to convert the I want to convert the actual minutes to seconds. So I'm going to say times 60, or excuse me, times 1 minute equals 60 seconds to any number of decimal places. And that, in fact, gets rid of this minute here. But I also want to say that we need to get rid of the revolutions as well. So I'm going to also say that 1 revolution is equal to 2 pi radians. So then we'll have units of radians per second per second. All I have to do for that is take the 833.3 and divide it by 60. You can hit equals there if you wanted. And then you're going to multiply by 2 pi. So this would be 87.26. That's 2 extra sig figs. 87.26 radians per second every second. So the other result is alpha in radians per second squared is equal to 87.26 radians per second. Again, box this off, and that's part of the solution. The other part, they ask us what it, and this should have been, I should have included a bar on it because it was average acceleration. So I'll put those bars back on it now. Now the other part is through how many revolutions will it turn? Well, we know our kinematic equations are basically analogous to the linear equations, so that we know v squared equals v0 squared plus 2ax minus x0 is going to become omega squared equals omega 0 squared plus 2 alpha theta minus theta 0. So that's one way we could get it if we go ahead and assume the acceleration is alpha that we just calculated. Now, the other thing we could do, we could also use the kinematic equation in linear motion is x equals 1/2 at squared plus v0t plus x0. The rotational analog to that is theta is equal to 1/2 alpha t squared plus omega 0t plus theta 0. Again, either one of those equations would work fine. Obviously, you use the time and the average acceleration that we just calculated to calculate the theta with the rightmost equation, and then with the leftmost equation, we wouldn't have to use the time, but we would have to use the acceleration that we calculated. So let's just go ahead and do it using the omega squared equation. So what I'm going to do is I'm going to say 2 alpha theta minus theta 0 is equal to omega squared minus omega 0 squared. And now I'll also say that theta minus theta 0 is actually equal to omega squared minus omega 0 squared over 2 times alpha. And of course, we already stated that we're going to allow theta 0 to be 0, which is again not really a loss of generality in any way. So in this case, we can just go ahead and calculate what the actual uh, total rotation will be, theta. So we get omega squared, which is we found 25,000 revolutions per minute, but I really don't want to use revolutions per minute. I want it in radians per second. So I'm going to say times 1 minute is 60 seconds, and then times 2 pi radians per 1 revolution. So that should be my final omega. I got to square it, minus 0 squared. And then I got to divide all this by 2 times my alpha that I calculated, which I'm going to use the radian per second one, which is 87.26 radians per second every second. Again, these two are not sig figs. With this result, we can go ahead and calculate it. I'm going to take 25 times 10 to the third. I'm going to multiply that by 2 pi. And now I'm going to divide that by 60. And now I'm going to square that. And that gives me 685,000, 6,853,880. So it's 6,853,880 radians squared per second squared divided by 2 times 87.26 is going to give me 174.52. But I really only had 2 sig figs there, so these are not significant figures. And I also had only 2 sig figs up top, so these are not significant figures either. So if I take this 685,3,880 and divide that by 174.52, I get 3.9. Carrying 2 extra digits is going to be 3.927 times 10 to the fourth, and that result should be in radians. So that would give us basically in radians how much we got. Now all I have to do is convert that to revolutions if I wanted to. In principle, I could have left it as revolutions per minute, but then I would have had to use revolutions per minute in the denominator. It would have worked out, but still we get it. So I've got the right number of radians. Now all I have to do is say that 2 pi radians is equal to 1 revolution. So I can now, since that fraction is 1, it's okay to write that as the answer and then put multiplication after it because it's just times 1. So now I can find out that theta is actually going to be, if I can get my pencil to work, theta is actually going to give me the result of 3.927 divided by parentheses 2 times 3.14159, close parentheses. That gives me 6.250 times 10 to the third revolutions. And that is our final answer for the final part of this. So again, you could have possibly done it another way. I highly recommend you try putting omega in revolutions per minute and put alpha in revolutions per minute. Obviously, omega would be revolutions per minute right off the get-go, but the acceleration would be in revolutions per minute per second. You can see that there are obviously going to be some issues with that, and that some things might not cancel out, but it's worthwhile trying. And I'd also suggest you try it with the theta equals 1/2 AT squared. In fact, I'm going to go ahead and do that now. So let's just look at the theta just in case. The theta equals 1/2 alpha t squared plus omega 0t plus theta 0. In this case, we already established that theta 0 is 0. We said it started from rest, so that's 0. So this should actually give us the same result. And this time I'll actually use it in revolutions per minute per second. So I'm going to say that this is equal to 1/2. And now I'm going to say 83 point, oh, excuse me, that's 833, my fault. 833.3, and that is revolutions per minute per second times 30.0 seconds squared. You can automatically see that when I do that, the second squared is only going to cancel out with the second in the bottom of the revolutions per minute per second, but the minute is not going to do anything. So I ended up getting something weird like revolutions seconds per minute. And that's not very helpful. So we really want it ultimately to come out in minutes. So bare minimum, I should change the revolution per minute to revolutions per second, and that would work fine. So in here, I could actually choose to uh, divide the 833.3 revolutions per minute. I could actually divide that by 60 uh, before doing the 30, or I can do it afterwards. It doesn't really matter. So I'm going to say 1 minute is equal to 60 seconds to any number of decimal places. And that's going to give me theta is equal to zero point 0.5 times 833.3 times 30 squared. And then I'm going to divide it by 60. And that gives me 6,249. Actually, it's 6,255. And that turns out to be just in revolutions, which is exactly the same answer we had before. Obviously, in this case, I only had two sig figs, so these two figures are not significant figures at all. But we do see again that we got exactly the same answer, and doing it with the theta equals 1/2 AT squared, so on and so forth. So hope that helps you. Have a good day. Bye bye.